Good afternoon, ladies and gentlemen, and greetings from beautiful but very cold Vienna. We welcome you to our series Data Bites, which is a kind of a lunch and learn concept that we do once in a while when we have interesting topics. And needless to say, we have a very interesting topic today. We're talking about machine learning in Industry 4.0. And for that, I'm greeting Mr. Simeon Harrison, who is presenting today the latest and greatest in the research of machine learning in Industry 4.0. He is with EuroCC Austria, located at the Technical University in Wien, and he will explain more about that when he introduces himself and the organization he's working for. With that, Simeon, are you ready?
I am. Let me just quickly grab the screen and off we go. So hello, everyone. Thanks, Hannes, for that introduction. Fantastic. There's not much for me to add then in that case. Let me just wait till my screen pops up. There it is. So I'm from EuroCC Austria, which is the competence center here in Austria for high performance computing, big data, and artificial intelligence. And this is why I'm here today to talk to you about artificial intelligence in general. Let me just quickly give you a run through our services. We at EuroCC have a very special offer for you right at that moment. I'll post the link in the chat in just a second. That is, you can get our services for free if you apply for that. We can't provide everyone with our services since we have limited resources, obviously, but do try to get your spot and apply for this services bundle. So what do? We'll sit down together with you and make sure that your idea that you're having, what you'd like to implement, is actually feasible for working on a supercomputer. And we'll also get you HPC ready. That means we'll show you how to actually access a supercomputer, how to get your code running on a supercomputer, and how to parallelize your code. Since this might be tricky for you, especially if you come from an SME, we do offer you financial advice as well, because there are heaps of support out there from the EU especially. So we'll guide you through that jungle and you can apply for grants and so on. So once you have a proof of concept that you'd like to try and get running, we'll help you with that and give you project support along the way. And then most importantly, we'll give you access to a supercomputer. Here in Austria, that would be the Vienna Scientific Cluster, but we also have access to the European network of supercomputers in case you don't actually have enough resources in Austria, which I very much doubt, by the way. But we're also connected to a link of experts all across Europe. Every single country has its own EuroCC National Competence Center. So if you have a very specific problem, we can get you in touch with our colleagues who might have a different emphasis. So just so much for actually pitching what we are doing. So do get in touch with us. I'll just leave that up for a second so you can actually scan the QR code. Let me just also post the link in the chat to where we have that offer of our services bundle, and make sure you check that out. And with that, we can actually dive into the topic for today, which is machine learning in Industry 4.0. Let me just bring up my new set of slides. There we go. We do work with supercomputers, but my laptop is not one, actually. Right, so artificial intelligence and machine learning. Hannes, can I just get a thumbs up if you can see my slides? Fantastic, thanks for that. So let's go through the basics. What is actually artificial intelligence? Well, artificial intelligence is such a broad umbrella term that's used everywhere right now, and it's very hard to distinguish what it actually describes. so there are several subdomains in artificial intelligence. You can say that artificial intelligence wraps around everything that somehow mimics intelligent behavior by machines. But within these boundaries, you also have that subdomain of machine learning, which we'll specifically talk about today. And then within machine learning, what's all the rage is deep learning these days. So we'll also have a look at that. So as I just mentioned, artificial intelligence is just mimic behavior in general, but that does not really mean that a machine would actually learn. For example, in the 80s, we had these recommender systems, which every big company thought it really had to have. But what that basically was they just programmed a huge amount of rules into a computer, into a mainframe computer, and tried to get that information from these pre-programmed rules. And obviously that could come up with useful information and useful suggestions, but that's not what we actually usually understand nowadays with artificial intelligence when we mention that term. So we these days want actually an algorithm that can learn, that can train on data, and thereby actually come up with something that is, let's say, sometimes unexpected, but also intelligent. So in machine learning, the main goal of that is just to determine the pattern that our algorithm can find in the data. And there are several statistical models that are applied for that. For example, there's k-nearest neighbor, k-means clustering, the naive Bayes classifier, regression methods, and so on and so forth. So there are heaps of different mathematical, statistical methods that we use when we actually train one of these machine learning algorithms. So the idea is always that we pump in some data in form of numbers into our algorithm, and then hopefully get the desired result. And to begin with, we take an input sample of training data. That's just the training set that we have available that we'd like our algorithm to train on. But the tricky thing is at the beginning is to actually get that data into a form that we can then pump into our algorithm. So we need to transform that data and somehow extract the numbers from it, because basically what every algorithm needs is just a set of numbers, a huge set of numbers. So the first question or the first trick will be, how do we get these numbers from our training data and get it in such a form that we can actually use for our algorithm. And then the actual magic happens here. That can be, as I mentioned, different statistical methods. Here we just have a fully connected deep learning network just to show you what it could be, but that's not necessarily the case always. And in the end, we get some sort of output. And what we will do is we'll use labeled data, and we'll compare the labels of these data to the output we received. And this is where the actual magic then happens. We get an output function, and we get we have these labeled data as a function. And the difference of it is what we call the cost functions. That's where the algorithm goes wrong. And we try to minimize then that cost as best as possible and begin again with the next training step. And we do that until the output is good enough, at least for what we need in our special application. In deep learning, we use these what we call as neural networks. We speak of deep learning when we have several of these layers in between. So these hidden layers, that's where the magic happens again. before that, we just input our data, we get some sort of output, and in between is where mathematics takes over. So there are basically three different forms of machine learning. There's the supervised learning. That's what I just mentioned before already. That means we have data that is labeled. So for example, if I feed some images into my machine, then I might know, okay, this image is a cat and this image is a dog. So this data is already labeled, and I can tell the algorithm what the correct outcome should be. And this is what we call supervised learning. And this enables us to create that loss function that I just mentioned before, which then in turn, we can try and minimize as well as possible. There are different ways for doing that. And then try to get the best solution that we can with that limited amount of training data that we have. In unsupervised learning, we try to do something very different. This is actually something we can find within big data and the methods that are used in handling big data. So basically, you're confronted with these huge amounts of data, and you don't really know what to do with that data, or which features, which information that data actually holds. Maybe information you don't expect to find. So in that case, it's quite useful to run some algorithms that try to classify your data, find patterns in it, and separate different groups. That's the main idea in it. But you then take that information to use within your decision making, but it's very different to the supervised learning that we just previously saw. And the last form of machine learning that you can find out there is reinforcement learning. And reinforcement learning, again, is a very different kettle of fish to the previous mentioned versions. So in reinforcement learning, and that came up with game theories, the whole idea is to find rules, hidden rules within very complex seeming systems. So for example, if you imagine a chessboard, it's easy to tell a computer, okay, what are the rules of chess? How can each figure on the board move? But it's a very different thing in always finding the best solution to beat your opponent. And for that, you need reinforcement learning. So what it does is the computer just plays at random, and every time it loses, it gets punished. That just means in mathematical terms, it might just get a -1 reward, a negative reward. And every time it does something which leads to success, it gets a positive reward. So the algorithm tries to gain as many positive awards as possible. That's how it's programmed. And by that, it gradually finds the best solution for every single situation it has already encountered. So as you can imagine, in chess, there are heaps of different combinations, and that means these algorithms need to be trained for a long time. Now, obviously, if it gets to these games, you can't really play, let's say, as many real games as we've played in the past 400 years. But however, we can simulate the whole situation, and we can let the algorithm actually play against itself. And by that, it can also find these rules. Well, what applies to any game? A game is nothing else than a simulation. You can apply to many different kinds of simulations. For example, optimizing a network, or optimizing the supply chain of a company. So that's when reinforcement learning really comes to be important. So what do we do? What are the applications of machine learning? Well, a classic situation is just the face recognition. Today, actually, when I just fired up my laptop, it tried to recognize my face successfully, even though it was early in the morning. And that's just something that we know from our daily basis. Then in a very, you could say historically important application would be the handwriting recognition. For example, if you've wondered how the Postal Service sorts all these letters, especially in a time when most letters were still handwritten, also the address, well, that's machine learning as well. And actually we'll be looking at that during one of the courses, because that's one of these hello world examples in machine learning. Might of course be speech recognition. Let me just go through that more quickly. Or autonomous driving. Autonomous driving is one of these complex things, as I'm sure you know, which has not been cracked fully so far. So that's a combination of deep learning, for example, in there, but also reinforcement learning. Deep learning, for example, you might already have that in your car. Deep learning for recognizing the road signs that we have, for example, to know what the maximum speed is. Or to realize when a person suddenly crosses the road, so the car initiates the brakes. So you might already have that in your car. That's just classic computer vision. And by the way, we'll have a look at exactly these problems during one of the courses. But then again, to actually understand the rules of the road, that would be something for reinforcement learning. And in diagnostics, medical diagnostics, obviously machine learning is something that has improved our well-being a lot. So it's much easier now to detect malignant cells, maybe even from data that we as humans couldn't have detected it before. As a matter of fact, a friend of mine worked at the who worked at the Medical University of Vienna. He trained an algorithm that detected illnesses by just scanning the retina in the eye. So there are really incredible applications there as well. But basically, machine learning boils down to two main problems, more or less. So with reinforcement learning, it's a bit different, but otherwise it's just two main problems. Usually it's either a classification problem. So you want to, for example, determine which object that is, or you want to recognize a face, or maybe you want to let in your dog through the dog flap and not any other animal. Or it could also be a regression problem. And in a regression problem, we'd like to get a number out of the system. So for example, you might want to know what tomorrow's energy supply and demand is based on input values like sunshine, wind, temperature outside. Is it a public holiday or not? What time of the year is it? What was the energy supply demand for the last week? These are all input data that get into a model and then come up with a number with a demand. So that would be regression. And most problems fall into these two categories. Just to show you, give you a bit more of an overview of what these different methods are. So during the courses that we'll be talking about, that we'll offer in combination with EAT manufacturing, we're talking about supervised learning. We're talking about classification and regression problems. And these are the applications that you can find that. But we'll be also focusing a lot on problems that are based on Industry 4.0, or that's becoming more and more interesting for Industry 4.0. So that could be object detection that we're touching on, but that could also be predictive maintenance, for example, or time series analysis. So we'll be touching on these subjects, but more about that later. Okay, Hannes.
Very good. Simeon, thank you so much. There is already questions popping up. Before we go into those, I want to everybody to know, if you have a question, please use either the chat or the Q&A feature. If it's a question that you would like to discuss, raise your hand, and we're going to give you the opportunity to talk to Simeon directly. We're going to have an upcoming course on machine learning from May 8th to 9th, so 2-day course. My question here is, Simeon, what kind of learning methods, machine learning methods, will you cover in that course, actually?
Yeah, let me just, I've got a PowerPoint slide covering that. Let me just see if that works seamlessly. That's always one of these things. Now, probably need to share a new screen, just a second. There we go. Zoom tells me you can see my screen. Is Zoom right? Fantastic, okay. So yeah, there are different machine learning methods, obviously, and we can't cover all of these during the different courses that we have on offer. However, on that course that we're having on the 8th and 9th of May, which is machine learning in Industry 4.0, we'll be covering the following. So always depending on whether we're confronted with a classification or regression problem, we will begin with simple regression situations. And I'm sure most of you will know what a regression is, but a linear regression, for example, is where you try to fit a line as closely as possible to the underlying data in order to make predictions or forecasts from that. So your heap of data is just a heap of data, but once you have a function, you can actually compute things with that and get forecasts. Remember, that's just a simplified visual here. We're just working in these 2 dimensions, but obviously machine learning problems can be multidimensional. So if your input space is huge, for example, if you have input data that concerns the, let's say, the temperature, the pressure, time, if that's of an essence, and so on, it can become multidimensional, but obviously we can't depict that here. So that's why I took this simple representation. Sometimes it can also be useful to use more complex models, like, for example, the polynomial regression, as you can see here, a line which does not represent the underlying data closely. But beware, you can end in a situation where we have what's called overfitting. So if you have a situation like this, you might say, okay, the left graph here, that trend line looks much better because it closely represents my training data, right? And the right graph is just more of an approximation of what I'm having here. But however, if you apply these methods then to real data, not just your training data, but data that's out there in the real world where you would actually want to use your algorithm, you might find that, oops, that line that I created here, that very complex regression, does not really represent the real data out there. And my simple straight line, my linear model, does the job much better. So simplicity is often the key. And this is what we have on the left here, that's called overfitting. So I just perfectly matched my algorithm to the underlying training data, but it's no good as soon as it hits real data that's out there in the real world. So that's something that we really have to look out for in machine learning. And for that, we need metrics. So we'll learn all about different metrics to determine which algorithm is best, how long we should train, and how we can tweak the actual algorithm to get the best results. We'll also cover support vector machines. That's just another method that we have out there in machine learning. In that case, as it's depicted here, it's depicted for a classification problem, but actually you can use all these machine learning methods, both for classification and for regression problems, depending on how you tweak things, but more about that in the course. Okay, so how does the support vector machine work? Just very briefly. Well, if you want to classify two different sets of data as we have here, but again, that could be multidimensional, right? You'd like to somehow separate them, ideally linearly, so with a line, so that you can actually say, okay, I found a line and everything that's to the left of the line is most likely a golden, what is that, hexagon, and everything that's on the right looks more like a white or silver triangle. So I can already predict what something is according to on which side of the line it drops. And what we're creating there is we're creating this street. We're trying to find the widest possible boundaries so that we get a perfect prediction. Now that might be a hard margin classifier, as you can see on the left-hand side here, where nothing actually falls onto that street itself. And these points right at the boundaries that define where these boundaries run are called the support vectors. But very often, again, if you try to train a hard margin classifier, that leads to overfitting data. So again, you just learn your training data off by heart, so to speak. You perfectly adapt to that, but it's not good for real data. So you might want to allow for some error, or at least find a soft margin classifier, as you can see here, or even allow for margin violations. So it just generalizes better in the end. So that's support vector machines just in a nutshell. Sometimes you can't separate things linearly. Like, how would you separate that with just a straight line? It's impossible, but there are tricks out there, and we'll also cover that during our topic of support vector machines. So for example, you could add more features by increasing the feature space. That means you increase the dimension by 1. So if I first center my whole data cloud, and then, for example, take the square of that, you suddenly end up with a 3-dimensional shape. And you might have a situation like here, for example, where you suddenly can separate that with a plane, which is also a linear structure. So there are tricks that we'll learn about during our course with also with support vector machines. There are other methods as well, like decision trees. Pretty simple. So if you just decide according to certain features. So for example, if y is smaller than 3, let's say 3 is about here where we have that line. If I say no, then it's probably a y square. That means my y is larger than 3. If I say yes, then I might ask the next question, is x smaller than 2? Well, if yes, then I end up with a hexagon, or maybe if not, a triangle. And you can see these separations here, these lines in the graph to the right. So that's how decision trees work, and we'll be talking about that. However, sometimes you want to combine methods as well. This is what we call ensemble methods or ensemble learning. One of the most famous ones are random forests, for example, where you have different sets of predictors, so different sets of decision trees, like we just saw before, that with different settings, obviously, that work on parts of our data that has been randomly sampled, and that just increases the accuracy a lot, let's put it that way. And we use these methods a lot for time series analysis, for example. We often talk about deep learning, which is all the rage, but it's not always the best solution for every problem out there. Yeah, so I hope that answered your question.
Very, very well, though. So machine learning really, sounds and looks very exciting, and I'm absolutely sure that many people are interested in this seminar. However, you do recommend to join the seminar that we offer on the 3rd first, which is data preparation. And you're very outspoken about those requirements. Why is that?
Well, the main issue is obviously, actually, I will carry on. That's more about deep learning here, but I will carry on with this. Well, the main issue is how do you get your data into a shape that the algorithm can understand? And for that, you need to somehow turn your data into numbers first. And then there's always the question, what kind of numbers? So you might have to tweak your data so that the algorithm then performs at its best. And during that data preparation course, we'll just have a look at different methods of how to deal with a data set in the first place. So for example, simple things with what do I do with missing values and so forth. And then how do I transform all that data? It could be letters, it could be images, whatever. How do I translate that into something numeric, into a number? And just to give you an example, if you have a look at this image here, which is that's the this hello world example I mentioned before, where the algorithm recognizes handwritten characters. If you look at that number 2 here, if you try to translate that image into a number, you could say, okay, I can interpret this as a matrix, and that matrix has the size 28 by 28, because that's the amount of pixels we have here, because every single pixel is nothing than a number. So it's just a number from 0 to 1, which tells me how black is it or how white is it, and everything in between, which would be gray. So that would be something we could work with a matrix the size of 28 by 28, with the values of each pixel. Or if it's a color image, you might have what we call a tensor. So it's a 3-dimensional shape then already. So that would be 28 by 28. And we'd have these 3 different colored channels. Sorry about that, it's not red, green, and blue. Yellow just fitted my my topic here much better, but you get the gist. So it's for these 3 different channels. Now, if you have video data, for example, there might even be a 4th channel that you need, and so forth. So this is all about just transforming what we have into numbers.
Very good. I have a couple of other things that I would like to discuss with you, but let's go first to some of the questions that are already posted. Muhammad is asking, what do you think about the role of reinforcement learning and deep reinforcement learning in Industry 4.0?
Yeah, they more or less, they go hand by hand. So what has been discovered is that we often need deep learning before we can actually set reinforcement learning in such a way that it is useful. So what we need deep learning previously already is just to preset the parameters that the reinforcement learning bits can then use. So the applications would be, I mean, we won't be touching on reinforcement learning, and I've got colleagues who specialize in that. That's not my part of the field, I have to mention here. But what reinforcement learning is just really good at is at optimizing things that you can depict as a network graph. That's where it's just really good at, or where you can find rules that are just too complex. But very often you need deep learning before that just to get the reinforcement agent on track, because otherwise it would just take forever until it is successful, because to begin with, it just acts randomly. And to be successful, you need to guide it into the right direction. So that's how these two go hand in hand. And yeah, it's absolutely a very hot topic. So we are, in fact, we've been talking with EAT, manufacturing CLC, about reinforcement learning and further trainings as well. If there is interest outside, we might touch on something like that as well. So do let us know. Yeah, thank you.
We can create a course later this year on deep learning as well. There's another question from Alfred, who is asking you, what are the key factors to consider when selecting a machine learning algorithm for a manufacturing application?
Well, there's a lot of experience out there, and that's the tricky thing about machine learning in general, is that it's a lot of trial and error. But most problems have already been tried out in different situations. So I would first try and find out, okay, what's typical for your situation. As I just mentioned before with time series analysis, I just heard a presentation of a paper last week where they used deep learning for that. And time series analysis is just something that you use a lot in Industry 4.0. And in the end, it just turned out deep learning, as fancy as it is, it's just not worth all that needs to go into, because that's computationally expensive. And support vectors simply performed at least at the same level, and just made more sense because they're computationally less expensive. It doesn't take as much time and resources to train these models. So I would always find out, okay, what's already out there, for what's the experience levels for your specific problem. There's also this website, I think it's called Papers with Code. That's just a good resource to find out what might apply to your problem.
Very good, Simeon. Thank you so much. Alfred has another question, and he's asking, what are some challenges? I interpret that, what are the main challenges, because there are so many that manufacturers face when implementing machine learning, and how can those be addressed or overcome?
Well, the main challenge, and it's always underestimated, is the data preparation. So first of all, you need to get your data, and either you just have too much unlabeled data lying around, okay, then you can apply some big data methods, but it's just getting the data first of all. You need to have labeled data in most cases. So data where you actually know what the outcome should be. And then you need to prepare that data. So it's everything to do with feature extraction. So what's unnecessary in your data for an algorithm, what just makes it underperform, or maybe overfit and not generalize, and get it into that form to actually pump through your algorithm. Because obviously machine learning is the super exciting bit, but what takes the most amount of time, even if it might be pretty simple in its methods, but it's just tedious and takes a lot of time, is preparing the data. So if you have a project, make sure you plan enough time for that. That's probably 50% of the time. Yeah.
Very good. So in short, the old rule is still valid: garbage in, garbage out.
Yeah, absolutely, absolutely. Yeah, and that's very much so in machine learning. Yeah.
Okay, very good. There's another question which we're going to address a little bit later. You were talking about that you're using and actually providing potential access to interested parties to Austria's fastest supercomputer. not just during the courses, but also if somebody has a problem and needs support. Can you explain a little bit what is a supercomputer? You know, we are all working with fast laptops nowadays, but I guess that's a little bit more than that.
Yeah, I mean, essentially, without going into it too deeply, we don't want to be sitting here the whole day. But a supercomputer is just basically a connection of CPUs and GPUs connected within a very fast network. So while your laptop you're working on might have a CPU with, let's say, 4 cores on it, a supercomputer can have thousands of cores. So simply speaking, what takes a vast amount of time on your laptop can be done really quickly on a supercomputer. However, the challenge is to actually get your code in such a form that it can run in parallel. And that's the main challenge. That is very different to traditional programming. It's not super complicated, but you just need to know how it's done. Otherwise, you won't get any speed up at all. And what these supercomputers often also have is just accelerators in form of GPUs. And especially when it comes to machine learning, these problems are always, as you can also see on the screen right now, are in some form of a matrix or a tensor, and that's just perfect for GPUs to handle data. That's what they were initially made for, right? For images, and images are matrices. So for that, they're just perfect to use. We might actually not be working on the fastest supercomputer, but on the second fastest supercomputer, but that won't make any difference to me, to you, believe me. That's during the courses, that is, yeah.
Very good, excellent. There's a question, an anonymous question, 2 parts, and you can answer one, and I'm going to answer the other one. The first part is, who would you recommend such a machine learning course for?
Yeah, so what we are touching on here is the basics. So you might already have an idea. You know that you and your company should get onto that bandwagon of machine learning, but you've just never had any chance to actually get into it at all. So we'll show you the basics during these courses, and we'll also be using data sets that come from an industrial background or a production background, ideally. And by doing so, hopefully we'll just whet your appetite and give you ideas what you could use that stuff for. In the end, obviously, you need to go out there and try it out yourself on the data that you are confronted with. But it really just should show you the ropes.
That's one thing. The other thing is, and I'm joking about that, because ever since ChatGPT got into the news, it seems that every second person is an AI specialist. And I think if you have some more understanding of AI and machine learning, you can much better determine who can help you with that, and who is really talking about AI, and who is just having a business card saying AI.
Yeah, absolutely. I mean, with ChatGPT, now that you mention it, the whole idea there is already that you have a pre-trained model that you can then adapt to your needs. That's at least what they created it for. And we'll be looking at that as well, especially during the deep learning course, because very often you just don't have the amount of data to work with. So there are heaps of pre-trained models out there. So the idea is take one of these pre-trained models, might actually be trained on something very different that you might expect or that you want to apply it to, but then just tweak it a little bit so it works for your data set or your problem. That's called transfer learning, and that's what we'll be covering during the deep learning course in September.
Very good. The second part of this question was, is there a discount for students? So everybody attending this webinar will get an email afterwards with the training courses we provide to that topic, which includes a discount code for 10% for everybody. If you are working with or in an organization that is a member of EIT Manufacturing, we might even give you an additional discount. If that's the case, just send us an email and we're going to continue talking about that. So that was this question. When you do your training on the machine learning course on May 9th, 8th and 9th, what kind of programming language are you using there?
We'll be using Python. It's just the most widely used programming language for machine learning. And we'll be bringing you the content in form of so-called Jupyter notebooks. As a matter of fact, I might later be able to show you that in my browser. But yeah, we'll just go through these notebooks and they're very easy. So you already have documentation and code there, which you can use also after the course, because very often you just load it with information, but need to go through it again. So that's what they are great for. And you get an immediate output as well. So you can see what it does, what you're currently doing, which result that yields. And it just gives you a visual pretty quickly. And we'll also just use cells empty cells where you should do your hands-on parts and try out different methods and tweaking different hyperparameters and so on.
Very good. One portion of your presentation earlier reminded me of the book, The Outlier. And with that, there is a question from Marcus saying, will there be a section on anomaly detection?
Yes, actually, we'll touch on that very briefly in the data preparation bits, because that's something that you obviously need to take care of when you're confronted with data before you pump it into a machine learning model, but not in such a sense that we would use it for fraud detection, for example. That's more of a big data topic.
Okay, very good. Another question is, there might be still some folks who are interested in joining those training classes will ask themselves, what kind of prerequisites do I have as a participant to be able to follow those 2 days of machine learning in Industry 4.0?
Well, it would be great if you just have basic Python programming skills. I mean, you'll also be able to follow along if you don't have that, but I would make sure to just do a really, really brief introduction course. There are tons out there on the internet. I don't have one off the top of my head, but that would be ideal. And there's also maths involved, obviously. We'll try to keep it to a minimum, which is often tricky for us at the Technical University in Vienna. But it would be great if you still have your high school math somewhere in the back of your head. It just helps you to understand how these things work.
So what you're saying, my Fortran education doesn't help me really.
Actually, Fortran is still a very widely used language for high performance computing, but definitely not for machine learning. But yeah, if you have a programming understanding in general, then you won't find it hard, since Python is a very easy to use programming language. Okay,
very good. So, ladies and gentlemen, here you have the chance to still ask your questions, put it in the chat, put it in the Q&A, or raise your hand and ask the question, and Simeon is more than happy to answer those. There's a little bit of hesitation.
I mean, what I can also alternatively give you, if you're interested, I can just give you a brief overview of what we'll be covering in the deep learning course in September. Haven't really touched on that. But yeah, just give you.
There you go. There you go into computer vision, right?
Yeah, that's about computer vision. That's right.
So how are you going to make those machines see?
Yeah, well, you have to come for the course to the course to get to know that. But yeah, I still have my slides here. Yeah, I'll just show you. So if you if you have an input image, for example, like that fella here that you might already know, very often the first step is, as I mentioned, to get that into an appropriate shape. So you might have to resize the image if it's too large, and also maybe center it. There are algorithms that would do that for you. And basically what you then get is just pixel values between 0 and 1, as I mentioned before. And that's what you then feed into your algorithm. And for computer vision, deep learning is just the main staple to do it with. It's just ideal for that. It's just how actually our visual cortex works in our brains as well. So the idea is to take that matrix of numbers, pump it into your algorithm, and then get a classification, for example. So you might get a probability, like in that case. So with 80% probability, it thinks it can see Harrison Ford in there. With a 10% probability, Sean Connery, and so on. So the basic building blocks are that we'll also have a look at are convolutional layers. They extract certain features, certain patterns, lines, and so on. We'll be covering methods there in how complex these are. You can do them very coarsely or very, very complex ones. We'll be also trying to reduce the computational load, because that you get so many parameters in these neural networks. You just want to, for two reasons, reduce that computational load, reduce the size of your problem eventually, because otherwise it would be computationally expensive, would just take forever. And they also tend to overfit otherwise. So that's what we need to be doing. And then in the end, you pump that information into a function that basically then says which neuron will fire within your neural network. And by that, it's trying to learn. So convolutional layers, as I mentioned, try to extract these features. You might want to get one that detects the horizontal edges or the vertical edges. By the way, that's also what your photo processing software uses. So what's behind that? It uses a filter and it multiplies that filter with your image. It's a matrix multiplication, basically, and you get another matrix out of it. So that's, again, it's all about matrices and tensors, and that's where GPUs come in handy. And then you might want to reduce the complexity with pooling layers. So that's the full-sized image. You probably can't even spot the difference here. And that's the subsampled image that's been done by pooling. Happens also if you send an image over WhatsApp or Signal or whatever, it downsizes that image. So in the end, all that information that the matrix that results in is then flattened and pumped into a fully connected, some fully connected layers where you reduce that size even more, and in the end with these activation functions in between that determine which neuron fires and so on, you get a set of answers. And if you compare that to the true labels, because it's 100% Harrison Ford, we know that, right? You want to form that cost function that I mentioned previously as well. It's the same here in deep learning. And then you want to minimize that cost function as well as possible, get that new information, reset all the parameters within your network, and train again, and so on until the results are good enough. So one of these typical computer vision networks out there, and there are many architectures out there that have already proven their quality, is VGG Net 16. So that might use some convolutional layers, then max pooling layers to reduce the complexity, reduce the size of the tensor, then it goes on with new convolution layers and so on. And in the end, you've got that reduced complexity, and it should come out with a correct prediction. So here you have I think that's a CT scan, by the way, that's going in there. And we'll also use these architectures and also pre-trained models that are out there. That's the transfer learning I mentioned beforehand, and try to adapt these to and tweak them to the problem we have in hand. So yeah, that's what we'll basically be covering during the deep learning course.
Very cool. I have to admit, I'm one of those CSI fans, and I'm watching those shows, and I'm always amazed if they have some blurry picture of a parking lot, and then they're gonna zoom in on a plate, and suddenly, quote unquote, clean it up, and then they can see the plate number. Reality or just the Hollywood vision?
No, I reckon that is reality. I mean, when I travel to Vienna, for example, I stay at a parking deck. I go to a park and ride thingy that has my number plate registered. So when I go to the barrier, when I exit that park and ride lot, it just immediately reads my number plate, barrier opens, and I go through. So yeah, I guess it's reality.
Okay, very good. Do we have any other questions, Teresa? No more questions? Okay, somebody is asking if we're going to share your presentation afterwards with the attendees of this webinar.
That's fine with me. Yeah, I'll send it to you, and I'm sure you can find a way to share it.
Yes. Mm-hmm.
By the way, if you're interested, let me just show you my screen again. I just pulled up. I'm actually connected to the supercomputer here. And this is how we'll work with. So we've got these Jupyter notebooks that I mentioned before. That's how it looks like. It opens up in your browser, and you simply go through. You've got documentation, but then you also have code, and you can execute that code pretty easily, and just jump from one cell to the next. And then in the end, you might also have cells. I just pulled up a DASK course. That's a course on easily parallelizing problems. In the end, you might actually, or you will actually find cells where it's your turn to code and so on. So that's how we'll be running through these courses. So make sure you check them out. There's the website for the one on data analysis and data preparation. So if you missed that before, if you joined us a bit later, you can read through what we'll be covering there. You can read for the prerequisites and everything. So that one would be on May 3rd. Then we've got the 2-day course for machine learning for I4.0 on May 8th and 9th. And the deep learning course for computer vision, that'll be a 3-day course. And we'll also offer the data preparation course again in September, because it also applies for deep learning with computer vision. But yeah, that'll be from the 11th to the 13th of September. So yeah, make sure you check these out.
Excellent. Well, thank you so much, Simeon. Do we have any other questions? If not, I encourage everybody to look into those training programs. If you do have any questions, don't hesitate, give us a call or send us an email. We are more than happy to answer that. We would love you to join us for those trainings, and we are extremely happy if we can contribute to the artificial intelligence, machine learning community growing in manufacturing, because we think there are huge potentials and great opportunities for each and every company, as well as for each and every one of you individually. With that, thank you so much, Simeon, for this webinar, and I'm looking forward to have our first trainings on data preparation in March 3rd. I wish all of you
May 3rd, sorry. May 3rd.
I said March, I'm so sorry. May 3rd, thank you. Yes, it's May 3rd, when we have the data preparation course. And with that, I'm gonna wish you all a great Easter week. Enjoy your Easter weekend, and hopefully see you on May 3rd. Thank you, Simeon. Bye-bye.
Thank you, thanks for having me, bye-bye.